Hello, so this is going to be the last video and we're going to look through an example of a difference in the means using hypothesis testing. Okay, now this is probably one of the ways which hypothesis testing is most widely used. Okay, so in other words, you're just trying to make a comparison between two products, two groups, whatever you want to do. So let's suppose I have two batteries. I have battery A, and I turn over and I look at the packaging on battery A and I find that it has a mean lifetime of some value, okay, so mu1, let's say. And then let's also look at battery B, so another type of battery, and again I turn it over, I look at the mean lifetime, and I'm going to call the mean lifetime of that battery mu2, okay. So my null hypothesis says, so let's suppose that there's no difference in the two lifetimes of the two batteries. Okay, so each battery is equally long as each other. That's going to be my null hypothesis. So I'm going to say mu1 is equal to mu2. Okay, but let's suppose, just because I've used each of these two batteries, I think that battery 1 is slightly better than battery B. In other words, it lasts longer. Okay, so that is going to be my alternative hypothesis, that the mean lifetime of battery 1 is actually longer than the mean lifetime of battery 2. So even though each of these two batteries, they say on the back of the package there shouldn't be any difference between them, okay, same price, everything like that, but I think that actually one is slightly better than the other, okay? So I think that is my alternative hypothesis. So what do? Well, I need to back up my claim by collecting some data. So let's suppose I go out and I collect some sample data. I'll do the sample data in blue. I go out and I collect, let's suppose, 50 batteries of battery A. Okay, so a big box of battery A, and I find that the mean weight of this sample is equal to, let's say it's going to be equal to 300 hours. Okay, now let's also suppose that on this, on the back of the battery, and I managed to find out from the manufacturer that the true population standard deviation, sigma, is equal to, let's say, 5 hours. Okay, so let's suppose that's given. Okay, so we know what the population standard deviation is for battery A. Likewise, let's suppose that the population standard deviation of battery B is equal to 4 hours. Okay, so they're relatively similar. But again, I want to test this, so I go out and I collect a number of batteries of type B. So let's go out and select 60 batteries of type B. And let's suppose that the mean lifetime of those batteries is equal to 300 and, sorry, not 300, let's suppose it's equal to 290 hours. Okay, so again, this kind of is consistent with my alternative hypothesis, but I want to test it. Is battery B worse than battery A, or vice versa? Battery A better than battery B? Okay, so what I need to do is I need to see. Well, have a look. At the moment, what I'm saying is that mu1 is going to be greater than mu2. In other words, if I was going to draw these two curves, okay, so let's suppose mu1 is, so battery A is going to be blue, okay, and I'm going to put battery B in red, okay. So let's suppose at the moment this is what I think is actually happening, okay. So actually the normal curve, so the mean weight of battery 2 is worse than the mean lifetime of battery 1, battery A. Okay, so in other words, the curve lies to the left. That's what I want to test. Is there actually a measurable difference in the mean weights? Okay, whereas the null hypothesis is basically saying these two curves are the same. It's basically saying these two curves lie perfectly on top of each other. Okay, so here's how I set it up. Okay, I can combine it together into one normal distribution. So I draw out my normal distribution curve. And I want to say, is one better than the other? So in other words, I'm going to be looking at a left-tailed test, because you notice here it's going to be a greater than, so I'm going to be looking at a left-tailed test. Is mu1 actually to the right of mu2? So I'm going to be looking at a right-tailed test. Okay, and I'm supposing at the moment that I've got some mean weight in the middle. So mu1 take away mu2 is actually equal to 0. Okay, so I'm supposing that that is 0 at the moment because that is my hypothesis. Okay, you notice here that my hypothesis I can rearrange to say that mu1 take away mu2 is actually equal to 0. Okay, and this one I can rearrange to mu1 take away mu2 is actually greater than 0. Okay, so at the moment I'm saying that there's no difference in the mean weight. So in other words, the centre there is 0. Now what I'm saying is that actually it's greater than. It's lying some point to the right. In other words, it's a right-tailed test. Okay? So how am I going to do this? Well, first of all, I need to come up with a significance level. Let's suppose I want to test it at the 5% level of significance. Okay, so I want to test it at the 5% level of significance. How significant is this? Okay, so I need to first of all come up with my test statistic. So first of all, I need to test, well, is n greater than or equal to 30? Well, the answer to that question is yes. They both need to be greater than or equal to 30, which they are. So the answer to that question is yes. Otherwise, I need to use, obviously, the t. Okay, the answer to that question is yes. Do I know sigma for both? Okay, well, I know it's for battery A and I know it's for battery B, so the answer to that question is yes. Okay, so therefore I can get away with using the z distribution. Otherwise, I'd have to use the t distribution if the answer to that question was no. Okay, so I can get away with using the z distribution here. Okay, so I need to calculate my test statistic. So just remember, my test statistic is given by, well, let me write it down. It's going to be x1 bar take away x2 bar, okay, minus the hypothesized difference in the means. Okay, so the sample difference in the means, take away the hypothesized difference in the means. Then I'm going to divide by the standard deviation. Okay, so in this case it's going to be the standard error. If you remember, the standard error is going to be given by sigma 1 squared over n1 plus sigma 2 squared over n2. That's the standard error, right? We've seen that before. We've seen that before, just using the central limit theorem. Okay, so therefore I can calculate what this is going to be. So x1 bar take away x2 bar is going to be the difference in my sample mean. So 300 take away 290. Okay, then I'm going to take away mu1 take away mu2. Remember, this is what I currently accept to be true, which is the null hypothesis. So I currently accept that the difference in the two means is actually 0. That's the null hypothesis, right? So I'm currently accepting that it's equal to 0, so I'm taking away 0 there. And I'm going to divide that by sigma 1 squared, which is going to be 5 squared, over n1, which is 50, plus sigma 2 squared, which is 4 squared, over n2, which is 60. So I stick all that in my calculator and I find out what my test statistic is equal to. So here we go. So I get 300 take away 290, which is going to be 10. Okay, take away 0, all divided by square root of, let's go 5 squared over 50 plus 4 squared over 60. Stick all that in your calculator and you find the value comes out as 11.4. Okay, 11.4. What that basically means, so 11.42 in fact, what that basically means is that the difference in the two means should actually lie way out over here. So x1 bar take away x2 bar. Okay, so the difference in the two means is about 11 standard deviations away from the mean. Well, if you think about it, where does our critical value actually start? Well, I can find our critical value. Where does our critical region start? I can find my critical value. And I can do that by looking in my tables. Now, clearly I'm using the Z tables. Okay, so I jump over to my Z tables. I'm looking at 5%, and remember it's a right-tailed test, so the entire region is 5%. So what I need to look for in here is a more extreme value, which is 95%. Okay, so I'm looking in here for 95%, or as close to 95% as I can get it. So let's have a look, 95%, 95%, 95%. So it's going to be about 1.645. Okay, 1.645. That's my critical region. Okay, that is where my critical region starts. That's my critical value there. So in other words, anything more than 1.645 standard deviations above the mean, then I know that this is a significant sample. And in fact, because I have 11.5 standard deviations, near enough, above the mean, this sample is significant. In other words, I can reject the null hypothesis. Okay, so I can reject the null hypothesis in favour of H1, the alternative hypothesis. Okay, I might as well just look for the probability, but actually you know that if you look for the probability in here, the probability of getting a more extreme value than this is well below 1%. Okay, so it's well below 1%. So actually don't ever put it's equal to 0%, because of course the probability with hypothesis testing is never equal to 0%. It's just really, really small. So chance of obtaining a more extreme sample than this is really, really small. It's well below 1%. So just write it like this, below 1%. Okay, so in other words, the probability is well below 1%. In other words, this is a very, very extreme sample. Okay, it's a very, very small chance of obtaining this sample if there is no difference in the two batteries. Therefore, we can say it is likely that there is a difference in the mean weights, sorry, the mean lifetimes of the two batteries. And in actual fact here, we can go slightly further. We don't just have to say there is a difference, we can actually say that this is probably going to be true. Because if you have a look, our sample mean is bigger for battery A, is bigger than for battery B. So therefore we can say it's probably going to be the case that battery A lasts longer than battery B. So battery A lasts longer than battery B. Okay, so you always need to think when you're doing your testing for hypothesis, you always need to set it up something like this. I always encourage you to think about, first of all, is it a right-tail test or a left-tail test? Okay, and I do that always by drawing a curve. Okay, you then find the test statistic. This tells you the number of standard deviations above or below the mean you need to be looking. And remember, you always look to see whether it's a Z-test or T-test, okay? So it's the number of standard deviations above or below the mean, okay? In this case, it's 11.5 standard deviations above the mean, right? Whereas I'm saying that anything above 1.5 standard deviations, 1.645 standard deviations above the mean, is significant. So this is well above that, so therefore I can say that I can reject the null hypothesis in favour of the alternative, okay? And you always put it in context. So it's likely that there is a difference in the mean lifetime of the two batteries. So battery A lasts longer than battery B. Something like that is a decent way of presenting your data. So like I say, you really need to be aware of what hypothesis testing is actually doing. It's really just coming back to this core idea. It's basically saying, what is the probability of obtaining this sample which you get? You go out, collect data. What's the probability of obtaining this sample data given that the null hypothesis is true? If the probability is small, so less than the significance level which we choose, so 5%, 10%, 1%, whatever it is, okay, then it's unlikely that our null hypothesis is true, therefore you can reject the null hypothesis. Simple as that.